Hello everyone, welcome to the second lecture on electrostatic conductors for IITJEE. I am Dhiraj Madan. So in the last lecture, we looked at a few properties of electric conductors. So these are materials which allow us to conduct electricity. An ideal conductor is one, wherein you have an abundant supply of electrons, and ideally, it should be infinite number of electrons, right? So these electrons can move under the influence of electric field, and that's why they are able to conduct electricity. But in the specific context of electrostatics, there are a few interesting properties which they have, and those were the ones which we discussed in the last lecture. So the first property was that whatever be the electric field, external electric field you supply, the electric field inside the electrostatic conductor is going to be zero. Inside the conducting medium, it's going to be zero. Why is that so? The reason being that if the electric field was non-zero, then these electrons would experience a force and hence they would be moving, and this wouldn't be an electrostatic condition, right? Now you may find this reason a bit sort of ad hoc, but we can go further into the details. The idea is that if you supply an external electric field, then the electrons are going to move under the influence of this field, and as a result the configuration of these electrons will adjust such that overall the electric field is going to be zero. So the electrons would move, they would deposit on the surfaces, they would create their own new electric field which will oppose the original external electric field. As a result, the net effect would be the net electric field is going to be zero, right, inside the conducting medium. So that's what is the more detailed reason if you want to understand that. And essentially the idea is that the electrons are going to move until they reach a configuration wherein the net electric field overall cancels off the external one. Right? So essentially these charges are going to be induced on the surfaces, and that goes by the name of electrostatic induction. So that was the first property. Okay, so in summary, the electrostatic field inside a conducting medium is zero. The second property is that there is no sort of charge which can exist inside the conducting medium. Why is it so? Because, well, if there is a charge, then essentially you can apply Gauss law around that free charge, right? And if you apply Gauss law, we have just said it in the first property that the electric field inside the conducting medium is zero. So essentially on the surface also the electrostatic field is going to be zero, which means that if you apply Gauss law, integral of E dot dA is going to be zero, which means that Q enclosed has to be zero, right? Because integral of E dot dA must be Q enclosed over epsilon naught. So overall the charge density inside the conducting medium must be zero. So whatever charge exists, it must exist on the surface. And now since there is no electrostatic field inside the conducting medium, so any 2 points if you take, they are going to lie at equal potential. Why? Because if you take any path from one point to the other, then essentially along the path, right, if you move along the path, the integral of E dot dl is going to be zero. So essentially Vp and Vq, they have to be equal, right? So because Vq minus Vp is minus integral of E dot dl. That's for the definition of potential. So essentially Vp and Vq, they have to be the same across all the points inside on the conductor, right? Because any 2 points, there must exist a line which joins these points. That's what we are assuming, right? And the fifth and the final property is that the outside the surface, the electrostatic field must be perpendicular to it, right? Why? Because if there is an electrostatic field along the surface, then essentially what would happen is that, so firstly, the electrons would experience a force along this direction and they can move along the surface, right? So that wouldn't be possible. The other way to understand it is that, so in the last property, you have studied that Vp and Vq, they are going to be equal. So essentially, since Vp and Vq, they are equal, so essentially integral of E dot dl must be zero across the line, and if there is an electric field, then it would be non-zero, right? So that will contradict the previous property. So you can understand it in several ways, but just to summarize, so we have 5 properties. Firstly, the electrostatic field inside the conducting medium is zero. Second property, no charge can reside inside the conducting medium. Third property, any charge which is there must lie only on the surface. Fourth property, all points on the surface are at equal potential. Fifth property, electrostatic field just outside the surface must be perpendicular to the surface, right? So inside the conducting medium, there can be no electric field in static conditions, but on the surface, there can be a component, but it has to be perpendicular to the surface. And there is in fact a relationship between the charge density of the surface and the electrostatic field, which is just outside the surface. That property we look at in the in one of the next few lectures. Okay. So we also studied a very simple problem where it had a conducting solid sphere which had a total charge of Q, and we had to find the electric field and potential at points which are inside and outside the sort of sphere. And we solved this problem. We realized that all charge flows to the surface, and essentially, even though it is a solid sphere, it behaves as if it is just a spherical shell, okay, or just basically a hollow sphere, wherein this charge Q is uniformly distributed, and we computed the electric field and potential corresponding to it, right? So that was what we looked at in the last lecture. So in today's lecture, we are going to look at a simple problem, which will be an application of the topics we studied in the last lecture. So this is going to be a very interesting problem. Okay, so do try to solve it yourself, and let's see, okay, how much we are able to look at today. So it's going to be fun. Okay, so the problem is as follows, that a point charge Q, a capital Q, is brought at a distance four times R, okay, from the center of an uncharged conducting sphere of radius R. Okay. So the problem is to find the potential at point P in the figure. Okay, let me draw the figure. So this is as follows. So basically, there is an uncharged conducting sphere. Okay, the radius is R. Okay, so it is slide. So my drawing is not that good, but just assume that this is a sphere. Okay, or I can draw again maybe. So this point is P. Okay, and the radius of the sphere is R. Okay, and a point charge Q is brought at a distance of 4R from the center. Okay, so this is 4R. Okay, so what's going to happen is that when this point charge Q is going to be introduced over here, so essentially on this sphere, what's going to happen is that there are going to be some electrons which are going to experience an electric field, right? So essentially that there is an electric field which is due to this point charge. Okay, and in the presence of this electric field, the electrons of the sphere, they are going to move in the direction opposite to that of electric field, right? So the direction of this electric field is away from this charge. So essentially there are going to be some electrons which are going to move towards the surface, right? And they'll essentially try to move in the direction opposite to that of electric field. And when they'll move, they'll leave an equal or some amount of positive charge on the opposite side. right? So this distribution could be very asymmetric, right? But overall, what's going to happen is that they'll now change the sort of distribution. So this new charge distribution is going to create its own electric field, which is going to oppose the additional or the external electric field, right? So there is an external electric field which is there. And now in the presence of these charges, so basically this field is also going to get distorted a bit because this sort of these negative charges, they are going to create their own electric field, right? So this looks somewhat like a dipole, but not exactly, because you also have positive charges here. Essentially, you will have electric field going away from these positive charges also, right? So the situation is now going to be as follows: that inside this conducting sphere, the net electric field is going to be zero, because there is an external electric field and then there is an electric field which is created due to these sort of charges. Okay. So overall, the net electric field inside this is going to be zero. But now overall, this situation is so asymmetric that it looks that it is very difficult to calculate anything, right? And I'm asking you to calculate the potential at point P at this point. Okay, so how do you do that? Right. So it looks like a difficult problem, but if we use the properties we discussed last time, we can actually try to solve this. So let's see how. So essentially the idea is that, the potential at point P, right, is going to be same as the potential at the center O. Why is it so? Well, the reason is that these two potentials, why they are equal, is that so essentially on this conducting medium, we had seen that all points are at the same potential, right? So whether you take a point P or any point on this sphere, they are all going to have the same potential. The reason being that, if you draw any path joining P to O, the electric field along that path is zero. So basically, Vp minus Vo is minus integral of O to P E dot dl. That integral of E dot dl is going to be zero. So essentially, Vp and Vo, they are going to be equal, right? So that was the fourth property we saw last time. And why is this now useful? Because now you can calculate the potential at O very easily. The potential at the center, you can calculate very easily. The reason being that, so we know the expression for potential, which is that it is integral over dq over 4 pi epsilon naught r, right? So that is the expression for potential we know. And essentially, or if there are discrete charges, then it's sum over I qi over 4 pi epsilon naught ri. Okay. So basically now we have one discrete charge which is at a distance of 4r from the center, right? So this is going to contribute q upon 4 pi epsilon naught times 4r. But what about the charges which have been induced on the sphere, right? So essentially, the idea is that all these charges, they are at an equal distance from the center, right? So in this integral, this small r is just capital R, right? Because all the charges which have been induced on the sphere, on the spherical surface, they are all at a distance of capital R. And we can take integral just in the numerator, we can take R outside, capital R outside. And what is integral of dq, right? So integral of dq is just 0, because the overall this sphere was uncharged. So the amount of positive charges and the amount of negative charges, the net sum has to be 0. So this first term has to be 0 anyways. The second term is q over 16 pi epsilon naught r, and that is my potential. So this is my solution. This is my answer, that potential at P is q over 16 pi epsilon naught r. Okay. So now let me give you a homework exercise, right? So do try to solve it. So this is the first problem. So basically the same problem, but now what I'm saying is that the net charge, okay, so what if in the above problem, the solid sphere, conducting sphere, has a net charge of 2q, right? So instead of net charge of 0, what if the net charge is 2q and a point charge q is brought at a distance of 4r. So that remains the same, but instead of uncharged, this total charge is 2q. Then what is happen? Then what will happen, right? So what is the potential at point P? So the same problem, except that now you need to compute the potential at point P, but the net charge on the sphere is 2q. That's the only difference we have. The second homework problem now is as follows. Is that what if it is a disk of radius? So instead of sphere, what if it is a disk of radius r? So these are the two homework problems. Do try these yourself and let me know in the comments if you are able to solve them. Okay. So thanks a lot. Bye.